Okay. We have already done algebra of derivatives in last lecture. Now we are looking at composition of functions, and we are checking how do we find out derivative of a composition. Say for example, y is equal to log to the base e sin raised to 5x fourth plus 6. Okay, there is something called chain rule which you must be using, and that is precisely what we wish to develop. I mean, why should it work like that? That is what we want to find out. So the solution to this is chain rule. Okay, but then first we will have to establish why the chain rule will work. So basically what we are doing here is our variable is independent variable is x, and finally this is some function of x. Okay, composition of x. So if there is, what is our derivative, definition of derivative? Our definition of derivative is limit as x tends to c, f of x minus f of c upon x minus c exists and is finite. Then it is f dash at c. That is what is our definition, right? So if we write this definition in terms of h tends to 0, f of x plus h minus f of x upon h. Same thing. This and this is same. So what is this h exactly? It is, we can write it in this way. Delta x tends to 0. Change in the value of x is h. Delta x tends to 0. Then what are we trying to evaluate? We are trying to evaluate delta y upon delta x. My internet connection is unstable. Delta y upon delta x. Delta is change. Change in y. That is what is this in the numerator. Change in y per unit change in x. That is what is in the denominator. And the unit change in x is tending to 0. That is what is our limiting procedure. Okay. So this is what is our derivative, and therefore what we are trying to do is, instead of writing this big expression every time, what we are doing is we are writing this as ddx of y. This y continues to remain like this. But when we say ddx of y or dy by dx, we mean limit delta y upon delta x as delta x tends to 0. That is what is the meaning of this. So now suppose for 2, if I write a composition function, say z is equal to y of how do I write? G O F of Z. हाँ सर. हेलो हेलो. जस्ट फोनला काहीतरी प्रॉब्लेम. हेलो. हाँ सर. हाँ. हो हो. मी करतो फोन, परत बंद होतोय. मगाशी पण उपाध्याय मॅडम चालू होतं तेव्हा असंच झालं होतं. थांबा जरा. the chain that we have, in the chain that we have written here, f of x, then limit delta x, delta f of x upon delta x. I want to write it like this. Then delta f of x is delta y upon delta u into delta u upon delta w, delta w upon delta v into delta v upon delta x. We will have to write it like this: limit delta x tends to 0. This will be equal to, because y is operating on this function. Suppose we call this function as t. So y is operating on t. Therefore, limit delta y upon delta t, it will be, as delta t tends to 0, that will be the derivative of y. What is t? T is, that is t is u of this fellow. Do you understand this? It is going inside. So v of x is delta v upon delta. Suppose I have only one function like this and I am operating delta x, then it is delta v of x upon delta x. That is what is its derivative. But if it is w of x, if it is w, if the function is w of v of x, then it is limit delta w upon delta v of x, as delta v of x tends to 0. Correct? That is what is the derivative of this function. Then, but you do not know. I mean, you have a final variable x with you. Therefore, what we will do is multiply delta v of x by delta x. But in that process, what we are doing is we want to change this also. Check whether I am clear what I am saying, whether it is understood properly or not. One by one, if you do the composition, you will go behind by one step, but you are changing the variable. So if I really want to, eventually what is chain rule? Chain rule is, if this is the chain that I am producing, then it is, will I be able to say that, is this equal to limit delta y upon delta u, as delta u tends to 0, into limit delta u upon delta w, as delta w tends to 0, into limit delta w upon delta v, as delta v tends to 0, into limit delta v upon delta x, as delta x tends to 0. Maybe we know this only because we want to, and therefore, will we be able to say this equal to, as delta x tends to 0, limit f of x, or limit this entire composition? That is the question mark which we should answer. If we agree that yes, you can always do like this, then our chain rule is available. That means if you want to find out dy by dx in this case, then it is dy by du into du by dw into dw by dv into dv by dx. That will be your dy by dx. It is as good as your algebra. Even though these are not ratios, these are operators, but it will behave like a ratio in algebra. So we need to answer this. And therefore, let me write down the chain rule maybe for only two functions, because if it works for two functions, it will work for more than two functions because it is just a composition. So I write the theorem and we are going to prove it in two different ways, because there is going to be a limitation in the first proof, but that is easy proof. So chain rule. If functions f and g are differentiable and are defined by y is equal to f of u and u is equal to g of x, then composition function phi defined by y is equal to f of g of x is differentiable. हा बोला बोला हो मला तुम्ही पत्ते पाठवू शकाल का? मला काहीच माहिती नाहीये. कसं जायचं मला माहिती नाही. पत्ता पाठवला तर बरोबर. हा 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 बरं. किती वाजता? नाही, मी 11:30ला निघणार आहे खरं. मला काहीतरी अपॉइंटमेंट 2 ते 3 आहे. 1 ते 2 का 2 ते 3 अशी अपॉइंटमेंट आहे. चालेल 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 ठीक आहे. ओके ओके. The differentiable and we have dy by dx is equal to dy by du into du by dx. That is phi dash of x is equal to phi dash of u into g dash of x. This is what is our chain rule for two functions. Composition is FOG here. So variable, independent variable is x, u is dependent on x and y is dependent on u, therefore composition FOG. I give you little time to check whether you can write the proof of this or not, and then we discuss. The functions phi, f and g are given by y is equal to phi of x y is equal to f of u and u is equal to g of x. So phi dash of x is equal to limit h tends to 0 phi of x plus h minus phi of x divided by h, which is equal to limit h tends to 0 f of g of x plus h minus f of g of x divided by h. Which is equal to limit h tends to 0 f of u g of x plus h, let us call it as f of u plus k, some increment, minus f of u, because g of x is u. Okay, upon h. Now we have to do a little jugglery here, which is equal to limit h tends to 0, f of u plus k minus f of u divided by k into k plus h if k is not equal to 0. So we are dividing by non-zero quantity. Okay, so now we can split limit h tends to 0 now can I change this from h tends to 0 to k tends to 0, because unless I have k tends to 0 here, I will not be able to evaluate this limit. Is that right? However, what is k and what is h? If we substitute, we get the desired proof. This is equal to limit k tends to 0, f of u plus k minus f of u upon k into what was our k? K was our g of limit h tends to 0. It is g of x plus h minus g of x upon h. Okay, and therefore this is f dash of u into g dash of x, which is dy by dx, which implies dy by dx is equal to dy by du into du by. That is the way to present. Now there is some error in this and there is some jugglery. I mean, just because the final result is correct, we can get away with the proof, but the proof has error. So what is the error? We need to discuss on that error and go ahead. Maybe we do one more proof where there is no error. Now the interesting part in this is the final result is correct. Your path of achieving final result has some error in this way, and therefore we have to eliminate it. However, because final result is true, nobody is really bothered about how you have achieved it. But because we are learning all these things in very much detail, we need to figure out what is an error in this proof, how it can be eliminated, or can we write altogether a new proof by which we get our chain rule and there is no error in that. Okay, so we will do that, but then I ask you, what is the error in this proof and how do we eliminate so that we make this proof itself full proof? Let us look at this, whatever we have written here, this. Now here, if I want to call this as dy by du, then delta w must tend to 0. First of all, when I am writing delta f of x upon delta x like this, I am assuming that none of these guys which are sitting there in the denominator are equal to 0. Okay, so we actually captured it in this, k is not equal to 0, right? But then if k is equal to 0, then we don't have this chain rule. This chain rule is for k is equal to 0, or is it so, or it works for k is equal to 0 also? And if k is 0, then this, is it possible to go to k tending to 0 or it is equal to 0? So this will also be an illegal step if k is equal to 0. If k is equal to 0, it is going to be a constant function because k is a small increment in u. And if k is equal to 0, that means the g of x is a constant function. So if g of x is a constant function, then g dash of x is anyway going to be equal to 0, and therefore making this entire derivative of f dash of x is also going to be 0, or what? I mean, is it correct or what is it? So there are questions, and therefore even though this is a very simple way of looking at the proof of chain rule, more or less it is correct, but we just are not aware of these functions which we are handling, and therefore every time the denominator that we are doing, I mean, see, h tending to 0 is fine because we are aware of x. How is x doing? X is well behaved or not? But we are not aware of k, and if there are more than one functions, we are not aware of delta u, delta w, delta v, how they are behaving, because we need to know them because we are putting them in the denominator. And whenever you are putting an unknown quantity in the denominator, you can be in trouble eventually. And therefore, this is, I mean, this technically whatever we have written is correct because k is not equal to 0. And maybe we can finish by writing saying that the result is true if k is equal to 0 also. Why? Because if k is equal to 0, we need not have to do all these things. Anyway, you have a g function which is constant function, or maybe you use the final result like our punctured line that you have removed k is equal to 0 from the consideration and proved it for k not equal to 0, and then whatever result you are getting eventually, you cross check when k is equal to 0, and you will find that if k is equal to 0, g dash of x is equal to 0, making f dash phi dash of x is equal to 0, which is again going to be true. Therefore, if we can conclude this by saying if k is equal to 0, then g dash of x is equal to 0, implying phi dash of x is equal to 0, which is true. Okay. However, there is one more way of doing chain rule, maybe little interesting, little involved but little interesting, which we will do now. For that, we require Carathéodory's theorem. Okay, so let us first prove Carathéodory's theorem. Let me write down the statement. Let f be defined on an interval I containing the point C. Then f is differentiable at C if and only if there exists a function phi on I. such that that is continuous at C and satisfies f of x minus f of c is equal to phi of x into x minus c for x belonging to I. In this case, phi of c is equal to phi dash of c. F dash of c. Phi of c is equal to f dash of c. Now, you just first understand what this theorem is all about, and then we will have to prove it and then use it for proving the chain rule. I will give you an example by which we will be able to. First of all, f is defined on interval I containing point c. So c is in the interval. F is differentiable at c if and only if there exists a function phi on interval I, which that is continuous at c and satisfies this expression. Okay. So you will observe that f of x minus f of c upon x minus c, limit as extends to c, is derivative of f of x. So phi of c is equal to phi dash of c is going to be obvious. Only thing which is not there in this theorem is the limiting consideration and the ratio. I mean, the differential x minus c is not in the denominator, but it is in the multiplication. So what is the example by which I can explain you this theorem? The example is x cube minus c cube. Suppose that is what is our function, then f of x is equal to x cube. Okay, so what is f of x? X cube. What is f of c? X cube minus c cube is equal to phi of x. There exists some function phi which is continuous on I. So let us check the continuity. And then this is x minus c. So can we just write down what this phi function is? If we take out x minus c common, then we get x square plus c plus c square, right? So phi of x right now is equal to x square plus cx plus c square. And what this theorem is saying, that if you want phi dash of c, then it is 3c square, we know, because it is a simple polynomial. And what this theorem is saying, that phi of c is equal to c square plus c square plus c square, which is 3c square. This and this is same. And it will happen every time, provided f is differentiable at c, and if and only if you get y continuous at c. Okay, so this is what it is. Now let us try to write down the proof. Okay, if we define the function like this, then we have to prove that phi is continuous. Okay, so the continuity of phi So this is what is, if f dash of c exists, then we get this result. That is part 1. And part 2, okay, so now let me explain. This is what is the complete proof of Carathéodory's lemma theorem. As I have explained, maybe you have finished writing and then concentrate on what I am saying. Let me know once you finish. Okay, so this is what is the proof of Carathéodory's theorem. If f is differentiable at c, then we can prove that there exists a function phi which is continuous at c, and it is given by this expression. That is the first part of it. And if we assume that there exists a function phi which is continuous at c and is given by this expression, then the definition of continuity, if we use, we can complete the part 2 of it, and say that f is differentiable at x is equal to c. Now, this is important theorem because it is both ways, if and only if, and you will be surprised how this is used in proving chain rule, and that proof is going to be valid proof compared to earlier proof. So let me jump on to the proof of chain rule using Theodoris, and maybe in the next lecture, if you have not understood any of these steps in this proof, we can get into details and explain it, because now I have little less time. I would just complete the proof of chain rule. Now PB1, PB2, these were the two theorems that we have used to show the concurrency of perpendicular bisectors. We used PB1 twice and then converse once to show that they are concurrent. In case of angle bisectors, AB1, AB2. Similarly, this theorem is going to be very useful to us in proving chain rule. So, let me write down the chain rule for this again and write the proof chain rule. Let A comma B be subset of R. Let G be defined from A to R. Let F be defined from B to R. Let f of x be subset of A. Let C belong to B. If f is differentiable at x is equal to C and G is differentiable at f of C, then composite function GOF is differentiable at x is equal to C and GOF dash of C is equal to G dash of f of C into f dash at C. Proof. Since f dash exists, f dash of C exists by Theodoris lemma, there exists function phi on B such that phi is continuous at x is equal to C and f of x minus f of C is equal to phi of x into x minus for all x belonging to B, and phi of C is equal to f dash of C. Also, Since g dash of f of c exists, now this is part 1 of Carry theory. Part 1 of Carry theory. G dash of f of c exists. There exists another function psi on A such that psi is continuous at f of c, and g of f of c, g of f of x minus g of f of c is equal to psi of f of x into f of x minus f of c. बघा समजतंय का? We are operating Carry-Theodore's lemma two times, one for f dash of c and one for g dash of f of c. So part 1 to part 2, part 1 to part 2 here, and here also part 1 to part 2. Okay, now let us look at these two expressions that we have got. F of x minus f of c is equal to phi of x into x minus c, and gf of x minus gf of c is equal to psi of f of x into f of x minus f of c. So maybe this is expression 1 and this is expression 2. We can club them now and say, if we club them, we can say that g of by 1 and 2, g of f of x minus g of f of c is equal to psi of f of x into phi of x into x minus c. Is that correct? Phi of x into x minus c. So correct चाललंय. Ata, now if you look at this expression, what we have already proved is psi is continuous. So this is continuous and phi is also continuous. We have already proved this. Therefore, this is also continuous. So now if we look at this expression, we have got psi of f of x into phi of x as yet another new function which is continuous, and hence from 2 to 1 I can use Carry-Theodore's theorem in the reverse direction, saying that g of f of x is differentiable at x is equal to c, and if I just want to find out the value of g of f of x dash, then Carry-Theodore's lemma say that if you want to find out the value of this, then you evaluate this complex function whatever you have at c. Sorry, it is c पाहिजे. Then whatever this complex function is there, you should evaluate at c. So it is psi of f of c into phi of c. Is that right? But then what is psi of f of c? I think we have written it somewhere. Psi of f of c once we have done this 2 here, we should have written the meaning like this. Phi of c is equal to phi dash f dash of c. Phi of c is f dash of c. Like that, I missed one statement here. After 2, what statement we should write? After 2 here, what statement we should write? Phi of c. So psi of f of c is equal to the original function, which is g o f dash of c. बघा समजतंय का? The way phi of c is equal to f dash of c, that means if you substitute c in this function, you get derivative of this function at c, right? So similarly, if you substitute c in this function, that is what I am doing, you get derivative of, जरा neatly see this way, derivative of this function. You get derivative of this function. So after 2, this statement should be there. And now phi of f of c is equal to g o.
सर ते g dash of f of c असलं पाहिजे ना
इथे ना
हो
करेक्ट. आज माझं डोकं जरा ठिकाणावर नाहीये, तुमच्या लक्षात आलं असेलच. This should have been g dash of f of c. So I replace it over here, g dash of f of c into phi of c is f dash of. So the only interesting part in this is, because of this Theorem lemma, exactly similar to PB1 2 times and converse PB2. It happens exactly the same way. Now, because we have that Theodore's lemma ready with us, we could complete this in this fashion. Understanding that the theorem requires little time, and we need to really focus and find out whether every statement written in that proof is correct or not. But then guys who must have done these proofs for the first time must have spent good amount of time at that time. Okay, so this is what is our complete correct proof of chain rule, and we have done it for 2, so therefore I can extend it for more than 2. बघा समजतंय का? Otherwise we will do this theorem again on Thursday, no problem, but it is better you go through it, try to understand each and every step. It is involved, it is rigorous, but not very difficult. लिहून घ्या सगळं.